to lab number 6, Control System Engineering lab. In this lab, there are various lab tasks. We have to perform the various lab tasks in MATLAB. The first lab task is the representation of polynomial in MATLAB. How we can multiply polynomials in MATLAB. What is the command for the multiplication of the polynomials? In time domain is that is a convolution, CONV. Similarly, how to find the roots of the polynomial. Examples. Lab task 2 will be the partial fraction expansion in MATLAB. For example, you are having the differential equation, and that differential equation is converted to the transfer function by using the Laplace transformation. And afterwards, the Laplace, the transfer function is solved by the partial fraction method. And afterwards, the inverse Laplace transform of the transfer function is taken. तो उसके बाद जो इनवर्स लैप्लास ट्रांसफॉर्मेशन आप लेते हैं तो इस डोमेन से आप टी डोमेन में चले जाते हैं. That's why it's important to study the partial fraction expansion in MATLAB. Similarly, lab task 3 is how to find the root locus, Bode plot, and the Nyquist plot using a simple transfer function. And lab task 3 also involves the antenna azimuth position control system. How to plot the step and impulse response of the antenna azimuth position control system. And the transformation from the transfer function to ZPK, that is Z is zeros, poles, and gain. So alternatively, we can represent the transfer function by PF and ZPK. These are two methods. Okay, let's start the first lab task. And in this session, we will study the lab number 7 as well. So there will be two labs, lab 6 and lab 7. Okay, lab task 1, polynomial representation. We are having a polynomial P1 that is equal to 5s to power 4 plus 7s cubed minus 9s squared plus 2. So polynomial in MATLAB can be represented by writing just the coefficient in the square brackets. जो square brackets होती हैं उसके अंदर जो polynomial होता है उसके coefficient आप लिखते हैं. For example, the coefficient of S4 is 5, coefficient of the S cube is 7, and the coefficient S square is minus 9. Similarly, coefficient of S is 0, and the coefficient that is the constant coefficient that is equal to 2. So that is simple a row vector. Okay, polynomial multiplication. How we can multiply two polynomials? The two polynomials that is equal to P1 S cubed plus 7s squared plus 10s plus 9. P2 is S4 minus 3s cubed plus 6s2 plus 2s plus 1. And in MATLAB, we will use the command convolution. CONV, convolution. So P3 is equal to convolution of parenthesis, left parenthesis followed by the left square bracket. The coefficient of the polynomial P1, 1, 7, 10, 9, square bracket, the right square bracket, and here the coefficient of the P2, coefficient of the polynomial P2 in square brackets followed by the right parenthesis. So CONV convolution is used for the multiplication of the two polynomials. So let me execute the program by copying the program. Control C and Control V here in the command prompt. Let me write the CLC. Let me clear the command window. Control V. This is a P3 convolution of the two polynomials P1 and P2. and that is the result: 1, 4, minus 5, 23, 48, 81, 28, and 9. These are the coefficients of the polynomial P3. Okay, we are having a transfer function that is in the factored form. अगर हमारे पास कोई transfer function हो और वो factored form में हो, for example, the transfer function is equal to s plus 2 n to s plus 5 n to s plus 6. So we have to write the negative coefficient in the polynomial P3. So for that purpose, अगर हमारे पास हमने polynomial s plus 2 into s plus 5 into s plus 6 को multiply करना है, so we will and that polynomial is in the factored form, factorized किया गया हो पहले से. So we will use the command poly, left parenthesis followed by left square bracket, minus 2 for plus 2 plus minus 5 plus s for s plus 5 and minus 6 for s plus 6 polynomial, and that will be equal to 1, 13, 52, 60. So if the polynomial is in the we are having a polynomial, and we multiply the two the polynomials, we will use the command convolution, and that should be in the might be in the time domain as well. You are having a transfer function or a polynomial, and that is in the factored form. If we people are interested to find the multiplication of these polynomial, we will use the command poly, and we'll write the negative values of the polynomials. That is equal to minus 2, minus 5, minus 6, and the command is poly, poly. Okay, how to write the roots of the polynomial? Let me write how to find the roots. So in MATLAB, you're having a polynomial. So we will use roots are OTS, roots followed by the variable P3, polynomial P3. Let me write in the MATLAB. For example, we are having a transfer function, and a transfer function is, in a transfer function, the numerator is written, that is the numerator num variable. Num is equal to the square bracket. These are the coefficient of the numerator, minus 2, minus 3, and minus 5. Semicolon, then is the stands for the denominator, that is equal to square bracket, minus 4, minus 6, and minus 7. These are the coefficient of the denominator. And you people know that this is important. Denominator is important in case of the transfer function, because the denominator shows the denominator polynomial shows a characteristic equation. And when the denominator, the value of the denominator is equated to the 0, it will become the characteristic equation, and that will shows the poles of the system. Similarly, the numerator will shows the zeros of the transfer function. So let me assign SYS, the transfer function, that is equal to TF, that is equal to num versus den. It will calculate the transfer function of the numerator and denominator, and the values will be stored in the variable SYS. So that is the transfer function, 2s squared plus 3s plus 5 divided by 4s squared plus 6s plus 7. If we people are interested to find the poles of the SYS, so we will write POLES, poles of the transfer function SYS. So the keyword is not the poles, it is the pole, SYS. These are the poles, minus 0.75 plus 1.0817 iota, and this is the second pole. So I'm interested to find the zeros of the transfer function. What are the zeros? I will write the zero of the transfer function ses. These are the zeros. Similarly, I can write the roots. The command I can use alternatively. I can use the command roots for the den for the denominator. So the same. These are the roots of the den denominator. Roots are the poles of the denominator. So this is how we can write in MATLAB. Okay, going further, we are having the partial fraction expansion in MATLAB. We are having a transfer function f of s that is equal to b by a, and that is in the Laplace domain. That is equal to numerator by denominator. And if we can write the coefficient of the numerator and store it in the variable that is equal to num. You can have other variables for the numerator, num1, num2. You can might have other names for the variable. So, and similarly, the other variables is de and den. That is a0, a1, up to the an. The command used for the partial fraction expansion is rpk. rpk. RPK, square brackets RPK, that is equal to residue, 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 followed by the parenthesis numerator versus denominator, num versus den. Where on the left hand side in the square brackets, R shows the residue. For example, we're having a improper fraction, that may be proper fraction, and for example we assign that if we manually solve that, we assign some variables a, b, c, and that will be the values of the R residue. Similarly, the way p shows the poles of the partial fraction, and k shows the direct quotient by solving the proper fraction or improper fraction. So the k will be, or the proper fraction, the value of the k will be equal to 0. Or the improper fraction is that fraction in which the power in the numerator is usually greater than or equal to the power or the degree in the denominator. That the improper fraction is that fraction in which the degree of the polynomial in the numerator is usually greater than or equal to the degree of the polynomial in the denominator. So here we are having a example that is equal to s square plus 2s plus 3 divided by s plus 1 whole cube, and we have to expand s plus 1 whole cube. So that will be s cube plus 3s square plus 3s plus 1 then. The numerator here, num is equal to square brackets the coefficient of the s square, that is equal to 0. The coefficient that is the coefficient of s cube. 0 is the coefficient of s cube. 1 is the coefficient of s square. 2 is the coefficient of 2, and 3 is here. Similarly, in a den we are having 1, 3, 3, 1. The command is rpk is equal to residue num versus dim. So let me execute this program in MATLAB, and you people will see the result. Control V. So this is the value of this is a polynomial. Num is equal to 0, 1, 2, 3, den 1, 3, 3, 1. The values of the residue or the values of the coefficient A, B, C जो आप जिस तरह find करते थे partial fraction method में, 1 minus 0, that is 0 and 2. The poles are minus 1, minus 1, minus 1. Here 1 के अगेंस्ट द पोल जो होगा वो -1 होगा. सिमिलरली 0 के अगेंस्ट जो पोल होगा वो भी -1 होगा, और 2 के अगेंस्ट जो पोल होगा वो भी here -1 होगा. And the value of the k, that is equal to empty square bracket. So k is 0 here in this case. This is the proper fraction. So that's why the value of the k is equal to 0. For the improper fraction, the value of the k will be, there will be some value. This is example number 2. Again, you can solve it by yourself. Example number 3 is we're having improper fraction. So let me execute this program by copying it in MATLAB. This is the program. The coefficients are 2, 5, 3, 6, transfer function, and then the denominator 1, 6, 11, and 6. And the command used is rpk, residue. Control V. So here in command prompt, when executed, r is equal to -6, the residue is -6, -4, and 3. Against the poles, -3, -2, and -1. And here the value of the k is equal to 2. So if you people can solve it by manually, अगर आप इसको manually solve करते हैं तो आपको इसकी समझ आ जाएगी. पहले अगर improper fraction हो उसको proper fraction बनाएंगे, वहां पे 2 आ जाएगा, डायरेक्ट क्वोशंट की वैल्यू 2 आ जाएगी. इसके बाद आप प्रॉपर फ्रैक्शन आ जाएगा एंड यू कैन सॉल्व इट इन मैटलैब. इसमें मैटलैब में सॉल्व कर सकते हैं या इसको मैनुअली भी सॉल्व कर सकते हैं. ओके, सो गोइंग फॉरवर्ड, this is the Laplace 3. How to find the root locus plot, the Bode plot, and the Nyquist plot. Using the transfer function. An example taken is from the Norman S. Nice Control System Engineering book. This is the chapter number 8, example 8.7. The transfer function is g of s is equal to open loop transfer function, that is equal to s square minus 4s plus 20 divided by s plus 2 and s plus 4. Here in the numerator, you can see the numerator is in the polynomial form. So we may write directly the coefficient of the polynomial in the numerator. The denominator is in the factor form. So we might use the command POLY. First we will multiply these two and then it will be a polynomial. So let me copy. We are having the program in MATLAB. I can just write the I will use the editor window. Let me paste it over here. Okay, here's the program. CLC clear all, close all. Before writing the program, you have to clear the command window and clear all the variables, and similarly we have to close all the figures. In numerator, we are having the coefficient of 1, -4, and 20. What is the transfer function? Let me write the transfer function as well. Control C. Control V. Let me write a commit over here so the program may not execute. GFS is, this is the value of the numerator and denominator. So the num is here is equal to 1 minus 4 and 20. Similarly, the denominator is in the factored form. Factored form mein hai. So we will use the command TOLY minus 2 and minus 4. Then. Okay, that will be for plotting the transfer function. Let me write the variable sys that will be equal to TF transfer function parenthesis. Inside the parenthesis you may write num comma then. So the transfer function will be calculated in the command prompt. There is a no semicolon, so you can see the transfer function in command prompt. And similarly, if we can find the root locus RLCUS, root locus of the transfer function. So we will write the command RLOCUS, root locus sys, SYS. And that will be the figure number 1. Let me write the figure number 1 before the root locus. Similarly, finding the Bode plot, you will use the command Bode, and before the Bode, I will write the figure number 2. So there should be a separate window for the figure Bode of the transfer function SYS, having the name SYS. This figure 2. Similarly, figure 3, that will be the Nyquist plot. NYQUIST, Nyquist. SYS. And the last command will be a grid on. So let me execute the program. So this is the transfer function s square minus 4s plus 20, s square plus 6s plus 8. This is the transfer function. These are the plots. This is the first plot figure, that is the root locus. So this is the root locus. We are having 2 poles here, 2 zeros on the right hand side, and we are having 2 poles at minus 2, and the other is at minus 4, and that is in the on the left hand side. Similarly, we can find the Bode plot, and that is the magnitude, that is the log magnitude and the log phase. So that is given here. In the third plot is the Nyquist plot of the transfer function. This is the Nyquist plot by writing the command NYQUIST, Nyquist. So this is how you can just plot easily the root locus plot. You might have the Bode plot, you might have the Nyquist plot, and some other plots as well, if you know the transfer function. And that can be very easy in MATLAB. You just write the command, for example, in one line. That will be SYS followed by the transfer function TF, parentheses. Inside the parentheses, you might write directly the numerator coefficient here. For example, the coefficient here is 1 minus 4, 20. Similarly, you can write the coefficient here, square in the square brackets inside the parentheses. That will be 1, 6, and 8. So that will be the transfer function. Yes, this is the transfer function. Just you write in one line. Okay. Proceeding further, we are having a example, that is the Antenna Azimuth automatic position control system, that is in the control system engineering book, Norman S. Nice, and that is the chapter number 3. You may find it in the chapter number 3. Similarly, that is also in the chapter number 4. So this is the antenna position. This is antenna control. That is antenna azimuth control is example of position control system. You people are controlling the position, azimuth of the antenna direction. You are having two potentiometer, the input potentiometer, and the second is the output potentiometer, and these values of the output potentiometer, the input potentiometer are summed at the summer, and the error signal is generated. That error signal is forwarded to the power amplifier or the preamplifier, which amplifies that signal. Usually that signal is very the strength or the magnitude of that signal is low, so the power amplifier is used to amplify that signal, followed by the motor and the load. So that is the motor, and the motor transfer function is given here, that is 0.208 divided by s into s plus 1.71, followed by the converter. So the whole transfer function of these three blocks is equal to, that is 20 divided by s square plus 101.71 plus 171. This is the transfer function. What is the input to the transfer function? The input to the transfer function is voltage, and the output is the rotation of the motor, because this is the position control system example. So when the controllers provide signal to the motor, so the motor will rotate to the particular position, and that will be the output, and that will be the position theta naught, and that simply that theta naught, that the position of that theta naught is converted to the speed by the tachometer. In some case that is a tachometer. In some cases you might need a converter to convert that theta, that angular position, to the angular velocity or to the speed. This is the transfer function of antenna, that is the open loop transfer function basically, and the value is the equivalent transfer function of three blocks is given as 20. This is the transfer function in the factored form in the denominator. Similarly, that is s squared plus 101.71 plus 171. So to write a step response and an impulse response of the antenna azimuth position control system, this is the MATLAB. You may write here in the same program by just let me remove this. The transfer function is different. G of s, that is equal to, and let me put a comment over here. So here in the numerator, the value is 20.83. 20.83. The denominator, that will be the square brackets, because it's not in the factored form, which is in the polynomial form. And the coefficients are 1, 101, 101.71, 171. So that will be the sys. You can just directly write, you may write you can write the transfer function. Is that is equal to num versus din. Similarly, the step response, if you people are interested to find the step response of this system or this transfer function, that will be steps sys. So here, that is the transfer function in the command prompt. So here, that is the step response of the transfer function, that is equal to, that is starting from 0 and up to the values. Here, it is worth mentioning that यहाँ पे ये बात ज़रूरी है कि जो हम सिस्टम जो सिस्टम को स्टडी कर रहे हैं, इसके और इनिशियल कंडीशन 0 हैं. अगर इसी ट्रांसफर फंक्शन या इसी में यहाँ पे अगर इलेक्ट्रिकल सिस्टम्स हैं, यहाँ पे इलेक्ट्रिकल सिस्टम के अंदर अगर इसकी कुछ जे एनर्जी इन्वॉल्व है, विस्कस डैम्पर इन्वॉल्व हैं, और अगर मैकेनिकल सिस्टम है, इलेक्ट्रिकल, दिस इज इलेक्ट्रोमैकेनिकल सिस्टम बेसिकली, इन व्हिच देयर इज इलेक्ट्रिकल पार्ट, देयर इज द मैकेनिकल पार्ट, एंड देयर इज द थर्ड इज इलेक्ट्रोमैकेनिकल पार्ट एज वेल. So अगर उसमें कुछ इनिशियल एनर्जी स्टोर्ड हो इन द फॉर्म ऑफ जस्ट लाइक यू आर हैविंग इंडक्टर एंड कैपेसिटर और द इनर्शिया और द विस्कस फ्रैक्शन, तो ये 0 से स्टार्ट नहीं होगा. So here we are assuming in this transfer function that the initial values, all the initial conditions are 0. That's why the step response will be start from the 0 up to the step up to the steady state value. The steady state value that is equal to here 0.12. You may solve this manually. So यहाँ पे जो होगा वो आ गया, आप इसको भी solve कर सकते हैं by partial fraction method. So that will be 0.12. यहाँ पे steady state है, यहाँ पे जाएगा ये इसकी value. That is the time and that is the amplitude. Similarly, if you people are interested to find the impulse response of this transfer function, so I can write IMPULSE impulse. And you people know that this is the unit impulse, and the unit impulse, the value of the transformation, the S transform, the value of the in the Laplace domain, the value is equal to 1. Whereas the value of the unit step, that is equal to 1 over S. This is the transfer function, and this is the response of the unit impulse. This is the unit impulse, and that is the response of unit impulse. That is going to the final value 0. So that is a stable system. In a stable system, the natural response approaches to 0 is the time approaches to infinity. BBO. Bounded input, we are having the bounded input, and we are having the bounded output as well. Okay, so that's all we have in this lab number 6. Similarly, I have an example from the Modern Control Engineering book that is written by the Ogata. And here, in this system, this is a mechanical system basically. Example is 5.9 in the book, and that is equal to mx double dot plus bx dot plus kx, the inertia, viscous damper, and the spring constant mbk. The initial conditions are x is equal to 0.1, x dot is 0 is equal to 0.05 meter per second, and this is the transfer function. So let me write the transfer function, and that differential equation is converted to the transfer function. Here, the initial conditions are not 0. They are having some initial conditions which are given here. So let me copy this program, Control C. MATLAB. Control V. Okay, let me write the coefficient of in the numerator. 0.1 to 0.35. 0.35. Coefficients in the denominators are 1, 3, and 2. Here, in the numerator, we are having 0.1 s square followed by plus 0.35 s, and the value of the constant coefficient, that is 0. So let me write here 0. The missing constant, that will be the 0. Similarly, I can write 1, 3, and 2 here. So system transfer function, and let me write the step response of this transfer function having initial conditions. Having some initial conditions, तो इसको देखते हैं, इसका response, step response देखते हैं. This is the transfer function. And dynamic system line cannot simulate the time response of models with more zeros than poles. Okay, so there is a mistake here. This is 0.1 followed by 0.35 and 0. Yes, fine. So this is the transfer function 0.1 s square plus 0.35 s. यहाँ पे मैंने एक 0 ज़्यादा ऐड किया था अपनी तरफ से mistakenly. That is the transfer. This is the step response, and you people can see here रिस्पांस 0 से स्टार्ट नहीं हो रहा, बल्कि जो इनिशियल सिस्टम के अंदर वैल्यूज थी, जो अगर आप इनिशियल कंडीशंस को देखें, सो हियर इन द इनिशियल कंडीशंस x0 इज इक्वल टू 0.1. सो यहां से स्टार्ट हो रहा है प्लॉट, यहां से स्टार्ट हो रहा है 0.1 से, एंड एज देयर इज नो फोर्सिंग फंक्शन. ट्रांसफर फंक्शन के अंदर आप देखें इनपुट की वैल्यू 0 है. जो फोर्सिंग फंक्शन है, जस्ट लाइक उसकी वैल्यू ट्रांसफर फंक्शन में उसकी वैल्यू अगर आप डिफरेंशियल इक्वेशन को देखें तो आपको पता चलेगा हियर इज द फोर्सिंग फंक्शन इज इक्वल टू 0. ठीक है. सो और सिस्टम के अंदर कुछ इनिशियल वैल्यू है, तो ये 0.1 से जाएगा और अप टू द 0 हो जाएगा फिर. So these are all we have in the lab number 6.